The ABCs of spacetime. The realm of space and astronomy is filled with all sorts of complicated-sounding terms and phrases. Naturally, some of these big words and big-name concepts can be intimidating to people curious about astronomy and other topics concerned with the greater cosmos. Spacetime is one such term, and many folks' brains simply switch off when seasoned scientists rattle on about it as if they were speaking to peers in their field. Luckily, this video aims to start correcting that error and help you understand one of the most common phrases in astrophysics. Let's get started. The last 100 or so years have been a revolutionary period for astrophysics and our basic understanding of the universe. Before then, we'd long believed that space was a three-dimensional framework. Think of a 3D shape like a sphere. Its three dimensions are the x-axis, y-axis, and z-axis. For a cube, which has more conventional sides, these dimensions are more commonly known as its length, width, and depth, or height. Like cubes, cylinders, or spheres, the universe we live in is pretty much a giant 3D shape. The three dimensions you can move in are forward or backward, left or right, and up or down. Whether you're driving a car, lying in bed, or skydiving, you are inhabiting a space of three dimensions. Now, time was long held to be an entirely separate concept from three-dimensional reality in classical physics. Physicists define time as the progression of events and existence from the past to the future via the present. The basic universal unit of time, the second, is based on the frequency of cesium atom transmissions. But we won't get into that today. Whether time only moves forward and why it does so are still unsolved mysteries, hence why we're nowhere near the invention of time machines. The forward progression of time we are all familiar with is called positive time. Negative time, aka reverse time, is only a theory at this stage. In 1898, a French scientist called Henri Poincaré was the first to theorize that time could possibly be the fourth dimension of reality. He is widely credited with coining the phrase space-time and laying the foundations of relativity. In 1905, German theoretical physicist Albert Einstein came up with a theory that suggested that the speed of light was independent of the motion of all observers. He claimed that time and space were linked, a claim that is still at the center of his theory of special relativity. Confused? How about an example? Let's say we have two twins. Twin A hops on a rocket that travels at the speed of light, while twin B stays on Earth for a year. After that Earth year, the twin who went on the rocket will be slightly younger than the one who stayed on Earth. Moving through space at light speed slowed time down for twin A while time ticked on, normally for B. Though A and B think they experience time moving the same, it is actually relative to how they are moving through space. In 1915, Einstein followed this up with a theory based on how large objects could warp space-time through gravity. This was the general theory of relativity. Black holes, which are super-heavy objects with insane gravity, are the most common example for explaining the general relativity theory. Let's say you got close to the outer orbits of a massive black hole with gravity thousands of times stronger than Earth's. The black hole's gravity would slow your time down relative to time on Earth. In other words, to you, life on Earth is on super fast forward. To people on Earth, you're on super slow-mo. It's plausible that a few minutes outside a heavy black hole would translate to decades or even centuries back on Earth. That's relativity. So, in the grand scheme of the universe, Einstein was trying to say that placing, or locating objects, or people wasn't just a matter of where they were in terms of the x and z-axis, but also a matter of when they were. Therefore, reality is x, y, z, and time, the four dimensions that make up space-time. Think about it. When setting up an appointment, or even a date, how do you go about it? You probably suggest a location, right? Let's say you want to get to know your crush a little better. You'd ask him or her to grab coffee at your nearest Starbucks, for instance. But is coffee at Starbucks sufficient information? Of course not. The venue is just a spatial coordinate. You also suggest a time or temporal coordinate for the meeting or date, right? Say about 10 a.m. on Saturday or something. In this case, the Starbucks, a three-dimensional place, is the XYZ, and 10 o'clock on Saturday is the fourth dimension of the appointment. Another way of proving the link between space and time is theoretical time travel. Let's say there was a time machine that could send you 100 years in the past or future. It would not be enough to just enter time coordinates. Why? Think about it. The Earth rotates on its axis and orbits around the Sun. Simply setting a date and year would put you at great risk of landing in outer space and being killed by the lack of atmosphere. If you were lucky enough to land on Earth, there's still a great risk of landing in the middle of the ocean since 70% of the planet is water. So your time machine would need both temporal coordinates and spatial coordinates to make sure you and the time machine land in survivable conditions. While time machines are still firmly restricted to science fiction, we have made a machine that allows us to peek glances at the past of the universe. The James Webb Space Telescope, JWST, is a $10 billion collaboration between NASA, the European Space Agency, and the Canadian Space Agency, launched in 2021 as a successor to the famous Hubble Space Telescope, HST. Packed with more advanced technology, the JWST can see more than 100 times further than the HST, and it is optimized to see infrared rather than just visible light or UV. This optimization allows the telescope to see through space dust and reveal stars being formed. As you probably already know, the starlight we see at night was actually emitted years, or hundreds or thousands of years ago. Some of the stars that appear to be shining are long dead, but the light they shone when they were still alive is only reaching us now. Proxima Centauri, the closest star to Earth besides the Sun, is about 4.2 light-years away. That means the light we see from that star was emitted over 4 years ago and took 4.2 years to reach your eyes. Now, what the JWST can do is look at stars whose light is only reaching us thousands of years after emission. Not only that, but the speed of its infrared radiation allows it to see the formation of those stars, essentially seeing back in time. So far, the JWST has picked up phenomena like the Southern Ring Nebula, a trippy dust cloud from a dying star 2,500 light-years away. NASA claims the telescope can see as far back as 13.5 billion years ago and witness the formation of galaxies 180 million years cosmic time. If the JWST was positioned 66 million light-years away and pointed at the Earth, there's a chance it could see the tail end of the Cretaceous period, when dinosaurs ruled the planet. On that bombshell, we've reached the end of the video. Thank you so much for watching, and we hope you learned something about this cool topic. Please like and share the video, and don't forget to subscribe to help the channel grow. We look forward to seeing you next time as we bring you more amazing space content. Bye.